Hello, today is February 3rd, 2022. The following is my invited talk at conference Photonic West 2022, which held in San Francisco. My participation in there is fully virtual. I like this virtual style of conferences. In the presentation, I describe the technology for fabrication of low-loss plasmonic waveguide. I explain how to make low-loss plasmonic devices using both the plasmonically friendly metals like gold or plasmonic unfriendly metals like chromium. The goal is to make possible a fabrication of plasmonic devices which could be used in practical optical data processing devices. Also, I explain details of fabrication of plasmonic isolator and plasmonic modulator. Hello, my name is Vadim Zayats and from IS Tsukuba, Japan, and today I will talk about effective plasmonic modulator and plasmonic isolator, challenges of design and fabrication technology. The work is done in collaboration with Kyiv University, Ukraine. First, I will give you an idea about the operation principle of plasmonic device. This picture shows the design of plasmonic isolator as an example. An optical fiber is to input an output into the circuit. The silicon waveguides connect all components of the circuit. A part of silicon waveguide is etched out and metal is deposited instead. The metal is not transparent, therefore it blocks the direct light. However, a surface plasmon is excited at the bottom surface of metal. And if the structure is optimized, nearly all light is transformed from input to output. The cobalt is ferromagnetic metal. Its refractive index is different for two opposite light propagation directions. The structure can be optimized so that a plasmon is excited only for one direction. In this case, the device will be transparent in one direction, but light will be fully blocked in the opposite direction. Such a non-reciprocal device is called an optical isolator. I will start my presentation with a simple question: why do we need a plasmonic device? The answer is simple and straightforward. Firstly, because a plasmonic device is very small, a typical length of plasmonic device is about 10 micrometer. Secondly, because plasmonic device is very fast, the operation speed of 170 GHz already has been demonstrated. As I will show in this presentation, the operation speed of plasmonic modulator can be even much faster. Next, I will talk about importance of the size of optical components for dense integration. Similar to electronics, it is important to integrate all optical components into dense chip. In the case of electronic circuit, the size of MOSFET transistors is very small, and billions of transistors can be integrated into one electrical circuit. Because of the dense integration, the integrated electronic devices have a complex functionality at low cost. In contrast, the size of optical component is not small. It is a photo of random optical components on my optical table. The size is not small and they cannot be integrated. At present, there are two types of components which are suitable for dense integration. It is silicon nanowire and plasmonic components. For example, size of silicon-based disc modulator can be as small as 10 micrometers. Length of plasmonic isolator can be as small as 10 micrometers as well. Next, I will talk about a reduction of propagation loss of a surface plasmon. A metal absorbs light, and therefore the propagation loss is unavoidable for a surface plasmon. However, when design and fabrication technology of plasmonic device are optimized, the loss due to the light absorption by metal is negligibly small and does not degrade the plasmonic device. Still, the optical loss is a key issue for any plasmonic device and it should be carefully addressed. In the following slides, I will explain details of the technological methods for fabrication of low-loss plasmonic waveguide. We have fabricated and studied plasmonic structure for over 10 years, and the absorption loss has never been an issue as soon as the described technology was followed. There is a misconception that there are plasmon-friendly metals like gold, aluminum, and copper, because the absorption of light is weaker, and only they should be used for a plasmonic device. And there is a plasmonic unfriendly metals like cobalt, iron, chromium, and many others, because the absorption of light is much stronger, and this metal should not be used in a plasmonic device. This figure shows the calculated propagation loss of light propagating in the bulk of a metal using optical constant measured by Johnson and Christie. In fact, the absorption loss of the plasmon-friendly metals is larger than in the plasmon-unfriendly metals. The smallest absorption in the plasmon-unfriendly chromium, and the largest absorption in the plasmon-friendly aluminum. This figure shows the calculated propagation loss of surface plasmon propagating along a metal-silicon interface. Please notice the difference of used units. The absorption of plasmon is always substantially smaller than the absorption of light propagating in the bulk of metal. Indeed, the gold, aluminum, and copper have a substantially smaller plasmon propagation loss of about 1 decibel per micrometer at wavelengths 1.5 micrometer. For example, in the case of 5 micrometer long plasmonic device made of these materials, the essential loss due to metal absorption is about 5 decibel. It's still large, but could be acceptable for some applications. In contrast, plasmonic propagation loss is huge, of about 20 decibel per micrometers in the plasmonic structure containing iron, cobalt, and chromium. Even in 1 micrometer long plasmonic device, nearly all light is absorbed in these metals, and therefore such plasmonic structure cannot be used in PIC. So, is it true then about the plasmon-friendly and unfriendly metals? In order to answer this question, it's necessary to understand the reason why the absorption of plasmon and the light absorption in the bulk of metal are so different. This figure shows a relative amount of optical field in metal. In the case of iron and chromium, there is a large amount of optical field of about 5% inside of metal. In contrast, the amount is less than 0.5% in the case of aluminum. That is the reason why the plasmonic absorption is substantially smaller in the aluminum in comparison to the iron and chromium, despite the bulk absorption in aluminum is substantially larger. It's not only the bulk absorption by a metal, but also the refractive index of metal determines the absorption of surface plasmon. This figure shows skin depth in metal, this one, and this figure shows the penetration depth of the optical field into dielectric, this one. Both the smaller skin depth in metal and larger penetration depths into silicon are reasons why the relative amount of light penetrating into aluminum is much smaller than the penetrating in iron and chromium. Next, I will talk about how to engineer the propagation loss of surface plasmon. The amount of light penetrated into the metal can be engineered and reduced in more complex plasmonic structure, which contains more dielectric layers. For example, when a very thin SiO2 layer is inserted at the silicon metal interface. This figure shows the calculated propagation loss in this plasmonic structure versus SiO2 thickness for both plasmon-friendly and plasmon-friendly metals, the propagation loss can be reduced down to 0.01 decibel per micrometer at optimum SI2 thickness. The optimum SI2 thickness is different for each metal. Such loss means that for a 10 micrometer long plasmonic device, the absorption loss is only 0.1 decibel, which is negligible in comparison to the unavoidable coupling loss. This figure shows a percentage of light penetrating into the metal in function of the SI2 thickness. At the optimum thickness, the penetration is the smallest. These figures show the skin depths in metal and penetration depths in dielectric. If the skin depth in metal is practically independent of SI2 thickness, the penetration depth in dielectric increases substantially. It is reason 1% relative percentage of optical field in metal decreases with SI2 thickness. Next, I will explain how much the propagation loss can be reduced. Even so, theoretically, it's possible to reduce the plasmonic propagation loss to a ever small number. There are technological limitations which limit the possible reduction. The first limitation is fabrication precision and roughness of a thin and sorted dielectric layer. As you can see, the required fabrication precision is more severe for chrome, iron, and cobalt than for gold, aluminum, and copper. Another technological limitation is penetration depth of optical field into dielectric. It should not exceed about 10 micrometers, otherwise the plasmonic properties may become dependent on inhomogeneities of an imperfection of the substrate. It limits possible reduction to about 0.1 decibel per micrometer, at least for these metals. This slide shows the result of our experimental measurement. This experimental setup. Light is coupled from input fiber to silicon nanowire waveguides and acts into the plasmonic waveguide. Passing through the plasmonic waveguide, light is coupled again into the silicon nanowire waveguide and finally into the output fiber. This is this top view, this is silicon waveguide, this is plasmonic section. This figure shows a measured fiber-to-fiber transmission for different lengths of the plasmonic section. The transmission loss increases with the length of plasmonic section. From this dependence, the propagation loss of surface plasmon is evaluated to be 0.7 decibel per micrometer. The loss extrapolated to zero length of plasmonic section gives the coupling loss between plasmonic and silicon nanowire waveguides of 4 decibel per facet. The propagation loss is still above the theoretical limit, but is sufficiently small for application. For example, the achieved propagation loss in plasmonic structure containing plasmonically unfriendly cobalt is smaller than in conventional simple gold dielectric plasmonic structure. Additional contributor to plasmonic loss is the light scattering at the edge of metal. Because of substantial step between the refractive index of metal and dielectric, even a tiny roughness of metal edge may cause a significant light scattering and as a result a substantial plasmonic loss. This type of loss can be avoided by optimum in-plane confinement. We have fabricated and measured plasmonic structures with 4 types of in-plane confinement. The yellow color shows the calculated distribution of optical field for each type of confinement. Top silicon layer for SOI, which is shown in green, is used for the confinement. The fabrication of stripe-type confinement is the simplest, but propagation loss of surface plasmon in such structures is very high. It is because there is a substantial amount of plasmon optical field at metal edges and the light scattering is large. confinement of groove type, wedge type, and bridge type. All are effective to reduce the propagation loss of plasmons. Detail of use fabrication technology can be found in this reference. Because of the smallest loss and the simplest fabrication technology, we always use the bridge type of in-plane confinement. All plasmonic structure which measurement data are shown in this presentation are of the bridge type. Even so, the plasmon propagation loss can be reduced to a negligible value. The problem of high coupling loss between plasmonic and silicon waveguides remains the main obstacle for wide application of the plasmonic devices. The coupling of 4 dB per each facet is unacceptably large for many applications. We have unsuccessfully tried several methods to reduce coupling loss. It is difficult because of the large difference of distribution of optical field of surface plasmon and waveguide mode, and because of the length limitation of possible mode converter. One method to avoid the high coupling loss between the plasmonic and silicon waveguide is usage in parallel integration scheme instead of the series integration. We have already achieved a very good result for parallel integration. The insertion loss of 0.9 dB for the gap of 60 nanometers and 2 dB for gap of 250 nanometers. Next, I will talk about plasmonic isolator. The optical isolator is transparent in one direction and it blocks light in the opposite direction. It protects optical elements from unwanted back reflection. I have explained the operation principle of this in serial integrated design. For practical applications, the coupling loss had yet to be reduced for this design. Another possible design of plasmonic isolator is of ring type. The ring resonator is made of silicon waveguide and a plasmonic structure is coupled at bottom. You can see magnified here. Because of low insertion loss of the plasmonic structure, we still have observed rather narrow peaks. Since cobalt is magneto-optical material, the peak's position is slightly different for opposite propagation direction of light, and as a result, the transmission depends on the light propagation direction. Another possible design of plasmonic isolator is Mach-Zender type. The Mach-Zender interferometer is made of silicon nanowire waveguide. The input light is split into 2 arms of interferometer by 50% directional coupler. At output, the light from both arms are combined by second 50% directional coupler. There is a plasmonic waveguide in vicinity of each arm of the interferometer. For upper and lower arms, the position of plasmonic waveguide is different. This magnified view. Even so, 2 plasmonic waveguides are magnetized in the same direction. The magnetization direction are different in respect to light propagation direction. For the upper arm, the magnetization is towards the right hand. For the lower arm, the magnetization is towards the left hand. Therefore, light experiences the opposite magneto-optical effect in 2 arms of the interferometer. As a result, the phase difference between light passing each arm is 0 degree in forward direction and the 180 degrees in the backward direction. Therefore, in the forward direction, the light passes from the input to output. The unwanted reflected light in backward direction is blocked. This figure shows a measured fiber-to-fiber transmission for the output 1 and 2. Despite the plasmonic section, the on-off ratio is still substantial, 15 to 20 dB. Another possible design of plasmonic isolator is a non-reciprocal coupler. It consists of 2 coupled silicon waveguides and plasmonic waveguide between them. Light is coupled from one silicon waveguide into a plasmonic waveguide. Next, depending on the coupling parameters, light either is coupled back into the same silicon waveguide or is coupled into another silicon waveguide. Because of the non-reciprocal properties of plasmonic waveguides, the coupling between two silicon waveguides is different for two opposite light propagation directions. The coupler can be adjusted so that in the forward direction, the light passes through the same silicon waveguide, but in the backward direction, the light is fully coupled from one silicon waveguide to another. Therefore, the coupler operates as an optical isolator. Next, I will talk about a plasmonic modulator. There are two types of plasmonic modulator. The first type is model squeezing type with horizontal electrodes, in which light is squeezed into a very narrow gap between electrodes. The second type is modulated confinement type with vertical electrodes. The electro-optical material is inserted between electrodes in both cases. The merit of both types of plasmonic modulators is a small gap between electrodes, which is between 1 and 100 nanometers. It results in very strong electro-optical effect. Because of the strong electro-optical effect, the length of plasmonic modulator is as short as 10 to 30 micrometers. Since the modulation length is shorter than the RF wavelength of modulation signal, there is no phase mismatch problem, which limits the modulator operational speed. As a result, the plasmonic modulator is very fast. Its operation at 200 GHz has already been demonstrated experimentally. All three merits are closely related to each other. All of them are greatly important for photonic integrated circuits. This animation shows the operation of classical bulk-type optical modulator. An electro-optical material is placed between analyzer and polarizer. The electro-optical material rotates the polarization of light. The 90 degrees rotation is required to switch light on and off. The change of refractive index is proportional to the electrical field and therefore is reversely proportional to gap between electrodes at fixed applied voltage. To make the modulator to be more effective, the gap between electrodes should be as narrow as possible. However, in case of bulk modulator, the gap is limited to about 1 mm. Otherwise, the metal of electrodes would absorb all light. In order to accumulate the required 90-degree rotation, the modulator should be long, and long modulator inherits the phase mismatch problem and the slow speed. The gap of plasmonic modulator is narrow. As a result, it is short and fast. It does not have all those problems of the bulk modulator. This slide compares three types of electro-optical modulator with respect to the gap between electrodes. The bulk modulator has a wide gap. As a consequence, it is long and rather slow. It requires large modulation voltage. The conventional plasmonic modulator has a narrow 100 nanometer gap. It is short and fast. It uses moderate modulation voltage. The new type of plasmonic modulator has an even narrower gap of 5 nanometers. As a result, it is even shorter and faster and requires even smaller modulation voltage. I would like to point one problem for fabrication of the conventional plasmonic modulator. For the second fabrication step, it requires a planarization and RF lithography for the fabrication of the 100 nanometer gap in metal. It's not a fundamental problem, but makes fabrication technology more complex and expensive. In contrast, for the new designs, the lithography is not required for the fabrication of the narrow gap. About operational principle of plasmonic modulator of type 2. As explained earlier, The insertion of thin dielectric layer at the metal interface substantially changes the confinement of surface plasmon and as a result reduces its propagation loss. The confinement and the plasmon loss are very sensitive to thickness and refractive index of inserted dielectric layer. Even a small electro-optical change of the refractive index of this layer causes a substantial change of propagation loss and therefore the amplitude modulation of the output light. This is example structure which consists of transparent conductor ITO as bottom electrode, the phase change material GST as an electro-optical material and metal. The schematic graph shows the cross-sectional distribution of the surface plasmon at different voltage. At larger voltage, the confinement is stronger, and therefore the loss is larger. At smaller voltage, the confinement is looser, and the loss is smaller. It is another structure where an electro-optical polymer is used. This is rigorous calculations propagation loss for plasmon in the structure for different modulation voltage. The modulation of the loss is substantial. This is cross-sectional distribution of optical field in part of silicon waveguide and in the plasmonic part. At the applied voltage, the optical field of plasmon penetrates deeper into dielectric and therefore coupling loss increases. This additional modulation effect substantially enlarges the modulation efficiency for this design. However, as I mentioned before, the average coupling loss of 3-4 dB between silicon and plasmonic waveguide is a problem for this integration. The in-parallel integration might be a solution to avoid this loss. Compatibility for the in-plane integration is one of merit of this new design. The research on this topic is currently going on. In conclusion, details of technology for reduction of the propagation loss of surface plasmons were described. The technology allows to fabricate a low-loss plasmonic structure using both the plasmon-friendly and plasmon-unfriendly metals. We demonstrate a small propagation loss and moderate coupling efficiency for cobalt-based plasmonic structure. A very small insertion loss was achieved for parallel integration of silicon and plasmonic waveguides. Thank you. If you are interested in more details about this technology, please take a look at the preceding paper which I have described all the details. You can find me at my website, so its address is here. Next you go to publications and next, yeah, this one. Yeah, here I describe all the details related to this presentation. Photonic West website is here. I think you can find it without problem.